Okay, welcome to lecture. We'll get started here in just a sec. Give everybody a chance to get in. And we're continuing on with our last chapter, which is kinetics. So we'll give everybody another minute or so, and then we'll get started and pick up where we left off. Okay, so we've been talking about kinetics, and last time we talked about something kinetic related, but let's see. We talked about obviously how to calculate the rate laws, again from experimental information. Again, choosing two entries in those tables where you basically have one unknown and sort of everything else is constant, allowing you to figure out the orders from the experimental information. And as we saw, once you figure out those orders from the experimental information, you then can solve for the actual rate law with the orders, and you could also then determine the value of the rate constant from that. We also saw specifically different types of sort of reactions overall: first order, second order, and zero order reactions. And again, that first order sort of kinetics and equations that we saw, as we talked about last time, are really the exact same ones that we saw with nuclear chemistry. And that was our natural log of A equals natural log of A naught minus KT, with our half-life of the natural log of 2 divided by K. And again, there was a certain graph associated with that sort of first order reaction. And that is the natural log of A versus time, which yields you that straight line graph. And what do we typically associate with that first order? Now, we also saw some new ones, which was our second order, and then also our zero order, our second order being the one that is 1 over A equals 1 over A naught plus KT. And that also had a different half-life equation, 1 over K times the initial concentration, which again means that it obviously is dependent on the initial concentration in terms of the half-life. Has its own sort of graph, which is 1 over the concentration versus time. And that again yields you a straight line, but actually a positive slope in that particular case, in that situation. And lastly, we had our zero order, which is very similar in sense of the concentration time equation, which is the concentration equals the initial concentration minus KT, also having a half-life of the initial concentration divided by 2K. Also going to yield you a straight line, negative slope heading to the left there. And we have our concentration versus time is what we would graph in that particular case. So remember that a couple really important things from all that we talked about was obviously the idea of the units of, say, the rate constant. And remember that when you look at the units of the rate constant, it will tell you perhaps what order of a reaction you're dealing with. So typically our first order has units of 1 over seconds or 1 over a unit of time. Our second order usually has 1 over molar seconds, or 1 over molar, some unit of time. And our zero order has really the same units that you find for the rate, which is molarity over seconds. So as we mentioned a number of times, that they may not sort of tell you what the order of the reaction is, but you're supposed to sort of know that by simply sort of looking at the units associated with that rate constant and be able to determine that it's first order, second order, or zero order, and again use sort of the appropriate equation for that particular order. And again, here you want to make sure that you did obviously choose the correct one so that you will be able to solve it obviously correctly. We also saw that you could use a graphical sort of approach to figure out the order of a reaction, and it would be those three graphs that we talked about, which are the important things. Again, the first order graph, second order graph, and zero order graph. The one that would yield you the most linear line would be the order of the reaction. And again, using something like Excel or something like that, or a graphing sort of program, you can figure out the R-squared value and sort of determine which one is the closest to 1, and that would usually indicate the order of a reaction. Then we sort of moved on into the idea of activation energy and sort of how reactions occur. And the activation energy, again, is that sort of minimum amount of energy that's required for a reaction to occur. It's really that hill that the reactants has to climb basically to get to the other side. And it obviously is going to have an effect on how fast or slow a reaction would proceed based on sort of the size of the hill. So the greater the activation energy, obviously usually the slower the reaction would proceed. And obviously the lower the activation energy, that lower the hill it is to get from one side to the next, usually faster the reaction will take place. Remember that when we get to sort of the top of the hill there, in terms of the activation energy, that is what is sometimes referred to as a transition state. And reminder that as we go from reactants to products, what's happening is everybody is breaking apart all of their bonds, and they're starting to form new bonds on sort of the product side. So as we saw, when you get to sort of the top of the hill, the highest part you could go kind of in terms of energy, we have what is sometimes referred to as the activated complex or the transition state complex. And a lot of times this is usually a very sort of unstable kind of species, something that doesn't hang around a very long time because, again, it has these partially made bonds, partially broken bonds, and sometimes we referred to as an activated complex or a transition state complex. And usually it kind of falls down in terms of energy relatively quickly to sort of the product side. It's also why it's usually, in a lot of reactions, very hard to sort of isolate that particular part of it because, again, it is not around a very long time, highest in energy, not very stable because of that. Now, the relationship, as we talked about, is obviously if we increase the temperature, what we have seen in terms of graphs and stuff is that we do see an increase in the rate constant, and that would make sense. Again, everybody has more energy when you increase the temperature, everybody gains more energy. There's a bigger proportion of molecules that can kind of get up to the other side. And in addition, more energy means they're going to be moving around a lot faster and obviously come in collision with each other a lot quicker, and the reaction would most likely sort of kick off a little quicker. That really led us into sort of the Uranus equation, which is basically sort of the equation that determines sort of the relationship between temperature and rate. And we saw and sort of finished last time on sort of one version of that equation, which is sort of the graphical version of it. And that's what we're actually looking at here on the screen. This, again, is basically an Uranus plot. And the equation that goes with this, as we've talked about, is the natural log of K equals minus E of A over R, 1 over the temperature, plus the natural log of A. And this, again, is in the form of Y equals mx plus b. So as we can see on this plot, on the Y, we plot the natural log of the rate constant. On the X, we do 1 over the temperature, which does need to be in Kelvin. And that, again, is what we plotted here on this particular graph. And as you can see on this graph, and what typically is the case, we will get a linear relationship that will occur there. And from that linear relationship, we will see that the slope is equal to minus E of A over R. And this works out okay because, as you can see from this line here, the slope, or the number of that slope, is going to be negative. So that negative there and that negative there is going to turn our activation energy into a positive number, which, as we talked about, activation energy is typically a positive number. So that all works out well, which means graphically speaking here, we can solve for the activation energy by almost simply multiplying the slope by 8.314 and making sure it's positive, right? And that is the gas constant that we use here, which is the one that's associated with energy. Obviously, when you do that, it's going to be in joules because R is in a value of joules. And that's, again, what you'll come up with. The other thing that we could actually solve for graphically as well is A here. And remember, A is the frequency factor. And the frequency factor is, again, sort of the proportion of molecules, if you will, that has the appropriate amount of energy really to sort of get up and over to the other side. So that's sort of what that is. And that is equal to the y-intercept. So again, we could use, like we did in this problem here, the y-intercept value. And again, it doesn't directly equal A, but it equals the natural log of A. So to get rid of that, you need to obviously take the E of both sides like we did there. And as in that process, when you sort of take the E of both sides, you're undoing the natural log part. So again, in terms of units, like we saw last time, the units end up being really the same units as the rate constant. Again, the units kind of go away when you do the natural log of it, but then when you kind of take the inverse of the natural log, they kind of come back. And again, that's why our A value here ended up with basically the same units as what we see with the rate constant. Any questions on any of those things that we talked about? So obviously, like I said before, you probably won't have to grab some graph paper and a ruler and do a graph. But you do need to, if again, a graph is perhaps provided to you with the equation, the R squared value and all that good stuff, be able to figure out things like, as we did in that particular problem, the activation energy, the frequency factor and so forth. Any questions on that? So most of the time it's not so convenient to do sort of graphs or plots, which a lot of times in this sort of experiments or kinetics experiments, we do a lot of those things. So sometimes it's better to maybe have a more mathematical approach to solving for activation energy and so forth. And we could do that with it, sort of another version of the Uranus equation. And another version of the Uranus equation is this guy here, sometimes referred to as sort of the 2-point form, which means if you have information about maybe 2 points, maybe 2 temperatures, maybe 2 and a rate constant, or maybe 2 rate constants and a temperature, maybe the activation energy, you could find another temperature, you could find another rate constant. You could use this to find the activation energy if you know 2 temperatures and 2 rate constants. So you could do those as well. So this one here, which is the natural log of K2 over K1, and again, that is just 2 different rate constants, equals E of A, which is our activation energy, over R, which is our 8.314 like normal. Just like also kind of normal, these are our 1 over temperature, which does need to be in Kelvin. And by the way, for some reason, people like to do weird things with this, but mathematically speaking, you should divide first and then take the natural log. People like to do some weird natural logging everything, then dividing, then natural logging again. So divide the inside, take the natural log of that product. The one thing you do want to watch out for in terms of units is these 2 guys here. The bottom guy, which is ours in joules. And as I mentioned, and we talked about last time, typically speaking, when we do calculate the activation energy, it is typically in kilojoules. So again, if you don't do a conversion there, you are going to find yourself sort of off again by that factor of 1,000, which may be even more complicated when you start doing natural logs or inverse of natural logs and stuff like that. So again, it doesn't really matter which way you go on that conversion. If you want to convert the kilojoules to joules, you can do that. Obviously, you can convert the 8.314 into kilojoules, but you do need to do some type of conversion for both of those units to make sure everybody like normal is in the same sort of unit. So obviously here something's missing, and one of the popular things to be missing, like I said, either a temperature you're trying to find, a rate constant, activation energy. Again, you could do this without sort of graphing and more of a mathematical sort of approach to solving it. I will say that the version that we see here of this equation is one version of this equation, and there is probably like 3 different versions of this exact equation that you will sometimes see. And the main difference really comes from sort of this parentheses part over here. Sometimes people will get a common denominator there, so like T1 times T2, and you'll have a variation on this sort of equation. Sometimes people will kind of distribute out the negative to the outside, and that ends up flipping things around, like where the T1s are here, they become the T2s, and the K1 becomes the K2, and so forth. So if you do kind of look it around, and I don't recall off the top of my head, I think maybe your book uses this version of it. But if not, there are sort of 3 different versions of this equation. If it is a legitimate version of this equation, that all should come out the same in terms of the answer. It's just that sort of distribution of things sometimes are a little bit different in terms of the formula that they use. So again, if you see the equation looks very similar to this, but slightly different, it just has to do with, like I said, sometimes people will distribute out the negative to the outside and so forth. So just keep that in mind. All right, so why don't you give it a go here. The reaction here has a rate constant of 2.57 at 701 and 567 at 895. Find the activation energy here in kilojoules per mole. So take a moment or two and see what you come up with. Okay, so let's take a look here. So again, we're going to use sort of our mathematical approach here. So that's going to give us the natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. Now, in reality, it doesn't really matter sort of which ones you call twos and ones, as long as you keep them together, you know, that information. So I'm going to call this K1, which means by default, this guy here will be T1. This will be my K2. And again, by default, that guy there would be my T2. So again, it really doesn't matter which ones you kind of make ones or twos, as long as I mentioned, you kind of keep the numbers together. So that's going to give me the natural log of my K2, which is 567, divided by my K1, which is 2.57, equals E of A, which is what we are solving for, my 8.314, which is my gas constant. 1 over the first temperature in Kelvin, which they already done that for us, so we don't have to worry about that, so that's good. A little 701 minus 1 over our second guy also was converted in Kelvin for us, so that is good. So doing a little bit of cleaning up here on the left-hand side, 567 divided by 2.57, a little natural log action there. Going to get us 5.39645 equals E of A over 8.314. If we clean up the parentheses there with the temperature, 1 over 701 minus 1 divided by 895. And it looks like inside here we get 0.000309215. So we're going to multiply the 8.314 to the other side. We're also going to divide by the 0.0003909. And if we do that, we will end up with a number. And we're going to divide by that and times 8.314. It gives us something like the E of A, bringing everything to the left-hand side, 145096. The units here would be joules because of the gas constant, which I didn't write there. And if we want to kind of clean it up, usually again, kilojoules is typically what we sort of end up with in terms of the activation energy. 145 kilojoules. Really, the only kind of unit that will cancel out there is our Kelvin, and we'll end up with our kilojoules per mole. And we do get a positive value here for activation energy, which again, as we mentioned, is typically what you should get is a positive value. As you saw from those graphs that we saw yesterday, again, the hill always goes up in energy, so should be sort of positive. Has to go up and over that hill, sort of endothermic. Any questions on that calculation there? Okay, why don't you try another one here? I think you got. So as we talked about earlier, the reaction, for the most part, a lot of times will double in rate if we raise the temperature by 10 degrees Celsius. So why don't you calculate the activation energy for that? And here's a couple of samples that you could use for that relationship. So see what you come up with. Okay, so here, again, they didn't really give us some values for the rate constants or anything like that. The idea is that the rate would double, and that's what this little hint here is. If the rate doubles, then the second rate constant will be twice as much as the first rate constant. Again, the rate constant sort of indicates how fast or slow, right, a reaction is taking place. So we'll double it here. They just sort of randomly chose some normal-ish type temperatures, and we went obviously up by 10 degrees Celsius. Obviously, if you subtract 273 from each of those values, there will obviously be a difference of 10 degrees Celsius. I think it's like 27 and 37 we're talking about in terms of the temperature. So again, here we pretty much have everything except for E of A. So if we use our equation here, we'll have the natural log of basically 2. And again, we get that from that relationship there, that basically, I'll go up here with it, K2, which would go on top, is 2 times K1 divided by K1, gets us the natural log of 2 on that side, equals our E of A over our R. And again, we'll use their temperatures. So I believe it was 300 there, right? So 300 Kelvin. Our T2. Our natural log of 2 on the other side is our 0.693. Again, E of A over 8.314. If we clean up what's in the parentheses there, 1 divided by 300 minus 1 divided by 310, going to get us something like 0.000107527. Don't feel like rounding. And at this point, we're going to do the same thing. We're going to take the 8.314 to the other side. We're then going to divide by that guy to the other side. And if we do that, we will end up with an E of A that is equal to, again, this is going to be in joules because of R. And again, if we kind of clean it up, we're going to get something like 53.6. 53.6 kilojoules per mole. Also, again, a positive number here, as we would expect for our activation energy. And really, if you sort of pick any sort of 10-degree window, within sort of room temperature-ish, which is 25 or normal temperature, you'll get around this. So for example, if you went 37 to 47, I think you get 56 or 57 kilojoules. So, it's around that ballpark roughly in terms of the activation energy. It will obviously change a little bit, obviously, if you increase the temperature or sort of lower the temperature. Any questions on using the Uranus equation here in sort of a mathematical approach? Probably in most cases what you will be using it or how you'll be using it. Again, the graphical part of it you do need to know how to do, but probably in most cases in book problems, online problems and stuff like that, you probably will be using more of the mathematical version of this equation. Any questions on that there? Okay, so we're going to finish up talking about mechanisms and sort of how reactions possibly could sort of take place. So just a reminder that when we talk about a reaction, there's really those two things that sort of have to occur. And again, it's sometimes referred to as sort of collision theory, and hence the idea they need to come in contact with each other. So our reactants do sort of need to come in contact with each other, but they do have to do it in a special sort of way. They do need to hit each other sort of in the right orientation, so sort of the active side, if you will, for that reaction to take place. And as we've been talking about, in addition, they need to sort of hit each other with the appropriate amount of energy to sort of kick off that reaction, to basically start being able to break bonds and start making new bonds, which is basically that activation energy. So they got to hit each other with enough energy to hopefully help them get up and over that hill to the other side. So as you see here in sort of this picture, it demonstrates the idea that not all collisions will actually result in products being formed. So just simply, you know, two things sort of running into each other isn't necessarily enough for a product to be formed. You do have to sort of meet those other minimum guidelines, if you will. You need to have that right amount of energy, and again, you need to sort of have the right orientation of those guys bumping into each other. So in this sort of diagram here, the purple circle there, which is the iodine, needs to kind of come in contact with the potassium so that it can form basically potassium iodide and release the CH3. And in the other case, if sort of the carbon side hits the potassium, it's not going to result in any type of products being formed. So again, sometimes we think, you know, they just need to kind of run into each other, but much like a lot of things, it does need to sort of happen in the correct way to allow products to be formed. And possible ways that reactions can sort of take place are steps where reactions could possibly take place. These are what we refer to as really mechanisms. And reaction mechanisms are sort of basically tentative explanations or possible paths to a product being formed or an overall reaction basically taking place. And usually in a mechanism, it will incur several individual steps along the way. And those several individual steps are what are referred to as elementary steps or elementary reactions. And it's very similar to almost like the idea of like Hess's law when you sort of add up all these parts to make an overall reaction. So usually a mechanism will involve multiple steps. And again, the idea there is if it's a good mechanism or maybe a possible mechanism for a reaction to take place, there is sort of a couple of important things that has to sort of happen, and we'll talk about those in just a second. But you know, obviously one very important thing would be you need to make sure that if you add up all the steps, it does equal the overall reaction. So they usually involve sort of adding individual steps together, which are these elementary steps. And obviously for a reaction to really take place, or this is possibly a good mechanism, you would need obviously to equal the overall reaction that you're looking at. So these sequence of elementary steps leads to product formation and is what's considered a reaction mechanism. And when we talk about a reaction mechanism maybe being a good mechanism, not such a good mechanism, what we're really sort of talking about in that sense is this, if it is a sort of good mechanism, quote unquote, what that means is this is a possible way that this reaction could take place. It doesn't necessarily mean that it 100% always will take place in these sort of series of steps, but this is a plausible, sometimes the word you hear, this is a plausible explanation or path to get you to sort of that reaction happening. So for example, the reason we need sort of mechanisms are the idea of like maybe these reactions really don't occur in a one-step process where we go from reactants to products, which is sometimes how we sort of get in our head like, oh, I see this one equation written and must just go directly, boom, from reactants, dead on to products. And a lot of reactions really don't happen that way. A lot of reactions are multiple sort of steps in terms of their overall process to get to the products. But sometimes we sort of focus in a lot on it's going to be sort of a one-step reactant to product sort of situation. And this is example here that we see up here is a good example of that. When we do this reaction of 2NO plus some oxygen to make NO2, during the actual process of doing this reaction, N2O2 is actually detected. And if it's detected in the process of doing it, it would have had to be made somewhere along the way. But we don't see it in the overall reaction when we look at it. So obviously in the overall reaction, which is this guy, we do not see any N2O2 present. So what that implies is that there must be some multiple steps that are happening for this reaction to take place. It also must mean that somewhere along the way, we should produce this guy. it also means in addition to it being produced, somewhere along the way, it's got to go away. Otherwise, it would still be present in the overall reaction. And this is a possible mechanism for this. And we can basically add both of these steps together. And here in the first step, they're saying that basically two NOs will come together and actually make that N2O2, which is why it can be sort of detected in this reaction. But in the next step that occurs, that N2O2 that is being made then gets sort of used up in the reaction. And that's why we don't see it in the overall reaction when it's all said and done. So if we add these together, just like everything else that we sort of added together in terms of reactions, anything that's on opposite sides of the arrow can cancel or get reduced. So in this case, the N2O2 would cancel out. And again, everybody on the left-hand side of the arrow will stay on the left-hand side of the arrow. Everybody on the right-hand side of the arrow will stay on the right-hand side of the arrow. And we do get the overall reaction that we see. The 2NO plus the O2 goes to the 2NO2. So this is sort of a plausible mechanism or explanation of how we get there. It also helps explain why when we do this, we see the presence of N2O2, but we don't see it turning up at the end of the reaction. And as we'll see in just a second, that is basically what's considered an intermediate. An intermediate is something that kind of shows up early on and then gets completely sort of used up by the time the reaction's over. And in this case, the N2O2 would be considered the intermediate in that case because of that. So again, here's just visually sort of the two-step process that is thought of occurring in this reaction. And again, the formation of that guy here, then we use it up here, almost like it didn't exist. But again, that's why we can kind of be able to test for it or see it in this process. And that brings us to, as I mentioned before, what is considered an intermediate. And as I mentioned, a very important part of something actually being an intermediate is what it says up there, and sort of what I described just a second ago. An intermediate is some type of species that basically shows up early on in a mechanism, but by the time the overall reaction is there and you balance the overall reaction, it pretty much gets completely used up. So that's a very good way that you can recognize something as an actual intermediate. It is there in the mechanism, but does not show up in the overall reaction. If you have something that's in the mechanism, and this could happen, you could have something in the mechanism where, you know, maybe you're able to reduce it down, it's made, and then it gets reduced down a little bit as you're adding the equations together, but it's still there at the end, then it's technically not an intermediate. So an intermediate cannot be present in the overall reaction. It has to be used up. And when we talk about these sort of elementary steps, we sort of talk about it in terms of the molecularity of it. And that's basically the number of molecules that are reacting. And there's a few different ways that we could describe these sort of elementary steps. We could say they're unimolecular, which means they basically have one molecule reacting. We could say that they are bimolecular, which means that they have two molecules reacting in each step. Or they could be termolecular, which means they have three reactions or three reactants happening. And you can see we don't typically go beyond that. And I think we might have talked about this yesterday as well. Again, in most cases, in terms of sort of the number of reactants that you're going to deal with, you know, one is common, two is common, three, you know, you're kind of getting to the outer limits. Again, we don't typically get, you know, 4 things reacting at once, 5 things reacting at once, you know, it's not usually the case in most reactions. And again, that's why when we were talking about sort of orders of reaction, like first order, second order, zero order reaction, you know, those are the common orders that we deal with, because in terms of, you know, reactants that are occurring or reactants that are reacting with each other, you know, 1, 2, 3 are sort of your max sort of reactants that you sort of will deal with. And again, in sort of the rare occasion, they're all like first order, you would have perhaps a third order reaction, but most likely some will be first order, some might even be zero order. And again, that's why sometimes when we talk about the overall orders, we sort of top out at second order because of that kind of rarity that you have all those sort of reactants happening together. So when we look at these elementary steps occurring, each of them have basically two molecules reacting. So they both would be bimolecular in terms of their elementary steps. So one thing that is also very different in terms of what we were talking about at the beginning of this chapter and what we are going to be talking about here with mechanisms is the idea of rate laws. Now, if you remember, when we write the rate law for a normal situation, not talking about sort of mechanisms, when we write the rate law, we do not use the coefficients as the exponents. But the one place that you actually can use the coefficients as the exponents is when you're dealing with a possible mechanism and these elementary steps. So for example, for this elementary step here, we could, if we wanted to, write a rate law where the rate would equal K times NO, and we would square it because technically this is 2NO, right? So the 2 actually would be used, again, for this specific purpose of mechanisms as the coefficient. And if we were to write a rate law for this guy, we would write the rate is equal to K N2O2, and I ran out of room there, and I'll just put the O2 down here. And again, the coefficients here are 1 and 1. So in terms of sort of coefficients as exponents, this is the only place really in kinetics where it is acceptable to take that elementary step and use those exponents for it. And again, it just gives you a way, because it's not really the overall reaction with all the multiple steps happening, but the sort of a snapshot of just that one individual reaction, it's okay to use the coefficients as those exponents. So again, like we talked about yesterday, you should not do that if it is not a mechanism situation. And then we see here again, as we can see on these examples, are rate laws that we could write for each of these sort of elementary steps. And this allows us and helps us sort of determine whether or not a reaction mechanism is a plausible sort of mechanism to occur. So how do we know if a reaction mechanism is plausible or maybe a good mechanism or not such a good mechanism? And the way we do that, there really is two really important things that has to happen in order for you to say, I think this is a good mechanism. And the two things that you pretty much have to have happen is, the first one is really important, is when you take all those elementary steps and you add them all together, you cancel out whatever cancels out on each side. You need to be left with, obviously, the overall reaction for whatever you're looking at. So if for some reason, when you add up all the steps together and you get a reaction and that equation doesn't equal the actual equation you're looking for, that would mean it's not a good mechanism. It's probably not a plausible mechanism. It is sort of a bad mechanism. If you add up all the steps and it does equal the reaction that you're looking for, then check mark, you're good so far. That means that this reaction mechanism so far is a good mechanism. Then the second most important thing is that the rate determining step, and the rate determining step we're going to talk about here in just a second, but the rate determining step is sometimes abbreviated the RDS for rate determining step, good abbreviation. And the rate determining step is the slow step in the proposed mechanism. And what the rate determining step is that slowest sort of sequence in a mechanism. And because it is the slowest sequence, it is really the step in the mechanism that determines the overall rate of a reaction. And the rate determining step, in order for it to help you determine if it's a good mechanism or bad mechanism, the rate determining step should always have a rate law for that step that equals the rate law of the overall reaction. And that is why we can use those coefficients, because ultimately the rate law is going to match that slow step, which has a certain sort of proportion, and it will match hopefully the experimentally found one. So very common type of question in terms of mechanism is in the actual question, they will tell you, hey, the rate law was determined experimentally to be this. And through some calculations, you need to go, okay, the rate law for my slow step is this. They both match. So check, this is a good mechanism. Or if you do it and the rate law doesn't match the one that's found experimentally for that rate determining step, then it would be a bad mechanism in that particular case. So those are really the two things that has to happen for it to be a plausible mechanism, quote unquote, a good mechanism, is when you add up all the steps, it does need to equal the overall reaction. And second, whichever one is the rate determining step, which should be the slow step in the mechanism, the rate law for that step needs to match the one that's found experimentally. Any questions on that? So again, it's sort of an idea like, you know, you're at the supermarket and you're in the 10 items or less, and the guy in front of you has got 40 items, right? So you're definitely not getting through that checkout stand until he goes through with his 40 items. He's sort of the slow step in the mechanism. And that's basically the idea here between the rate determining step. Now, there's a couple of different ways you could determine which one is the rate determining step or maybe not the rate determining step. But one way is easier than the other. A lot of times when you look at all the elementary steps in a mechanism, they will next to each step go parentheses fast, equilibrium, parentheses fast, parentheses slow. So that's, you know, the pretty easy way there. You take the one that's slow, and that should be your rate determining step. Another way that you might be able to determine which one is the rate determining step is, it again should have the same rate law as the one found experimentally. So in a case where they don't tell you which one is the fast step, the slow step, they will tell you the rate law that's been found experimentally, and then you can write the rate law for each step and find whichever one matches, and whichever one matches would be your rate determining step in the slow step in the mechanism, and also obviously the rate law for the overall reaction. Any questions on that there? All right, so let's take a look at some here. Boom. So I'll let you try this here. So for this particular possible mechanism, why don't you do a couple of things like I think it says on your notes. First off, why don't you figure out the overall reaction? Then why don't you figure out what is the intermediate or intermediates? And, you know, what is the rate determining step? So why don't you take a couple of minutes or two to try to think if you can sort of figure that out and see what you come up with, and then we'll talk about it. Okay, so let's take a look. So the first one should be very simple here, right? Guess I didn't need to write all that, huh? So to get the overall reaction, pretty much all we want to do is just add together everything, like we've done before. Anything on the left-hand side and the right-hand side of those arrows can cancel out. Anything that doesn't cancel out after that point, everybody on the left stays on the left, everybody on the right stays on the right. So if we kind of put a plus there, I'm going to see that my NO3 has got some canceling going on there. We got my NO2, a little bit of canceling going on there as well. And that's going to leave us, when it's all said and done, we got NO2 plus CO goes to NO plus CO2. So that would be the overall reaction here. Now, what is the intermediates? The intermediate is, in this particular case, NO3. It is only NO3. And you may ask yourself, but wait a sec, didn't I just cancel out my NO2 there? And the answer is yes, you did. But you did not completely cancel it out, right? So the NO2 did survive to the very end. And that makes it not an intermediate. So remember that an intermediate is something that is made early on in the mechanism, but gets completely used up by the time the reaction's over. And in this particular example, it is only the NO3 that gets made and then gets completely used up, and most importantly, not found in the overall reaction there that would be classified as an intermediate. So again, just because you could kind of reduce down something, if that guy still remains in the overall reaction, not your definition of an intermediate. Now, because these are both elementary steps here, we can write a rate law for each step. And if we write a rate law for step number 1, so I think I'm going to answer your question right here, okay? So when we do the rate law for each of the steps individually, because this is a mechanism, and as we've been talking about, this is really the only place where you can use the coefficient as the exponent. For step number 1, the rate law for that step would be the rate is equal to K times NO2, and we would square it. So to answer your question, yes, you would use the coefficient here in the elementary steps of a mechanism as the exponents. And again, the only place here in kinetics where you should do that is when you're doing these mechanisms. Now for step number 2, we could also write a mechanism, not mechanism, we could also write a rate law for it. And again, the rate here for step number 2 would be K times NO3 times CO. Okay. So these are our elementary steps and the rate laws associated with these elementary steps. And how is that going to help us determine, what is going on in this reaction? The other really critical piece of information that was given to us in this problem is that they said experimentally, the rate law was found to be the rate is equal to K NO2 squared. So if you remember from the last slide, the second most important thing was that the RDS, the rate determining step, or the slow step, should match the rate law in the experimentally found one. So the experimentally found rate law should match the rate law for the slow step or the RDS. So when we go to our rate laws here for step 1 and step 2, we could hopefully see that step number 1 has a rate law that matches perfectly. And what that means is step number 1 is the rate determining step, the RDS, or the slow step in this mechanism. And again, that is because the rate law that is found for the first step matches perfectly the experimentally found rate law. And that tells us that the step number 1 is the slow step. And by default, this guy would be the faster step. So it really is step number 1 in this sort of series of 2 steps that is determining how fast, or I guess how slow this reaction would also be occurring. Any questions on that type of mechanism question? So this is, again, a very common sort of mechanism question. This is a question where they didn't really tell you, hey, this is the slow step, this is the fast step. But again, they gave you that really important piece of information that the experimentally found rate law was K equals, NO2 over squared. And again, we could use that to determine which one is the slow step in this mechanism. And obviously, this would be one where this is perhaps a good mechanism, a bad mechanism. You can't really make that determination at this point, other than assuming that this is a good mechanism. Step number 1 of this mechanism, would be the rate determining step. And if this was, again, a plausible sort of mechanism. So let's take a look at a different type of mechanism problem. And this is one where we're going to try to determine whether or not this mechanism is a good mechanism, a plausible mechanism. Could this mechanism actually work, for this particular reaction? So in this one, we want to show that the proposed mechanism for the reaction of 2O3 goes to 3O2 matches the observed rate law, or that is a plausible mechanism. So these type of mechanism problems here, I don't know, they're kind of like, what do they do in those math? They used to call them proofs, I think. Like you fold the page and you got like one-sided hypotheses, observations, something like that, where you kind of know the answer, but then you got to prove that it is the answer, sort of thing. And that's sort of the type of mechanism problem this is, where we kind of know what the answer is that we're looking for, but we need to use the proposed mechanism to sort of prove that it is a good mechanism, or again, really a plausible mechanism, or maybe it's not such a good mechanism as well. So the 2 things that we really need to use to help us prove it is a couple of things that are given to us in the problem, and that is the overall reaction, which is 2O3 goes to 3O2, and the overall experimentally found rate law, which is this guy right here. So these are the 2 things. If we have an overall reaction that adds up to this, that's one check towards it being a plausibly good mechanism. If we find again that the RDS has a rate law that matches this guy that was found experimentally, that would be our second check that we need to say, hey, I think this is a plausible mechanism, a good mechanism. And again, if any of those 2 things really don't happen, then this would not be a good mechanism, not a technically plausible mechanism to occur. So let's just start with sort of the easiest thing to do, which is let's just add these guys together. So if we add both of these equations together, we are going to perhaps get some stuff that cancels out. It looks like an O cancels. And it looks like that is it, I think, in terms of cancellation. So what we are left with on the left-hand side of the arrow is 2O3. On the right-hand side of the arrow, we have an O2 there and 2 O2s there. That is 3O2. So that is a check to that part of it. So far, this is looking good in terms of, being a good mechanism. The first sort of hurdle was covered there. When we add up all the parts, it does equal the overall reaction, which is really good. Now, the second part is we need to determine is it still a good mechanism? Does the rate determining step, the slow step, match the one that's found experimentally? Now, we can identify this rate determining step very hard here. Not really. It is this one right here that says slow. Yes. So because they identified this one as the slow step, we know that that is going to be our rate determining step. What that means is when we take the rate law for that step, it should have the same rate law as the one that's found experimentally if it is a good mechanism. By the way, here, when we look at this mechanism, we do have an intermediate, right? And the intermediate here is O, right? So our intermediate in this one is O. So why don't we just go to step number 2, and step number 2, and if we write the rate law for it, the rate is going to equal K times O3 times O. And since this again is our rate determining step, what we're interested in is this guy here match this one here? And your answer will be no, don't look the same. And you may be right, but you may be wrong as well, by the way. And that is because, much like that old saying, right? If you want to compare something, you need to compare apples to apples, right? Oranges to oranges. I don't know, cheeseburgers to cheeseburgers, whichever one you like there. But you need to compare, you know, kind of the same thing. And we can't directly compare the rate law that we have here to the one that was found experimentally. And the main reason why is the one that's found in the elementary step contains this guy. And this guy, as we just mentioned, is an intermediate. So because it sort of contains the intermediate, we have no way to sort of directly compare the elementary steps rate law to the one that's found experimentally. So we have to do a little bit of math here. And really the purpose of this math is to get rid of the intermediate. So the goal here is to substitute out the intermediate for something else, and then hopefully get a rate law for this mechanism that has, you know, pretty much just the overall reaction guys in there and no intermediates involved. How we could do that is, so since we already used sort of the rate law for the second step, we need to then turn our attention here to the first step in the mechanism. You may also notice that the first step in the mechanism here is a little bit different in terms of the arrow. That is a bad computer generated reversible arrow, yes. So the first reaction here is actually a reversible reaction. It's a forward direction and reverse direction. And sometimes here they may even say equilibrium, right? Will be next to it. And once it reaches equilibrium, the rate of the forward reaction, like we talked about many times, will equal the rate of the reverse reaction. So we can write a rate law for our first step. But because it goes in both directions, we actually could write not just one rate law, we could write 2 rate laws for that first step. The first one is the forward direction. So I'll just write forward here. Going from, badly written forward, going from reactants to products. So if we did that, the rate would equal, I'll use K1 as they have there, the concentration of O3. Then for the reverse reaction, which is also occurring, in the reverse reaction, our products become our reactants, right, when it's heading in the other direction. So we would actually write the reverse reaction when it's heading in this direction. These guys here would be our reactants, which means the rate law for the reverse direction would equal K to the -1, O2, and O. So we have 2 rate laws that we could write for this first reaction, again, because it's a reversible reaction. Let us continue on, hopefully. Let me just kind of recap because I'm not sure where it just kind of died on me. I'm not sure if you heard any of that, but hopefully you did. So a reminder of what we were kind of doing here is we had our rate law for our slow step, which is our RDS. And the problem is we cannot compare it to the one experimentally because we did have that intermediate that's in there. So the goal here was to use the other step in this particular case, and it happens to be a reversible reaction. And because it does go in both directions, the forward direction and the reverse direction, and because when it reaches equilibrium, the rates of those two things will equal each other, we could write two separate rate laws for that first step. Again, one in the forward direction and one in the reverse direction. And we can then, where I was going with that is, because this first step will reach equilibrium, although we do not know what the rate number is here or the value of it, we do know that it is going to be the same number. And how that's going to benefit us is we could actually set the rate law for the forward reaction equal to the rate law for the reverse reaction. And if we do that, that would give us that K1 times O3 equals K to the minus 1, O2, and O. And the reason why that is beneficial to sort of set them equal to each other is we now can divide both sides by K to the minus 1, which gives us O2. And these guys are going to cancel. And ultimately what that gives us is that the concentration of O equals K1 O3 divided by K to the minus 1 O2. And hopefully you can see mathematically, we then could take what we just solved for and basically substitute it into our rate law for that slow step. So if we do that by substituting that in, what we're going to get is a rate law that now is the rate is equal to K times K1 divided by K to the minus 1 times O3. And now substituting in our other guys, O3 divided by O2. And now we have a rate law that is containing only stuff in the overall reaction, and we can compare it. And we could do a little bit of cleanup on this here. And if we do some cleanup, all three of these K values are the rate constant values, which means because they are rate constant, they're going to be the same number, which means technically speaking, two of them will cancel and you'll be left with just the K. Obviously, O3 and O3 times each other gives us O3 squared. So if we clean it up, we'll get the rate is equal to K times O3 squared. And 1 over O2 is O2 to the minus 1. Yeah. And what we see is now when we compare our rate law that we found from the mechanism to our rate law that we found experimentally. Get rid of some of that there so we can actually see it. We can now see that this rate law here found experimentally does in fact match the rate law that was on the slow step. And what that means is that this may not be the correct mechanism every single time, but it is a plausible mechanism for this reaction to take place. A, because the overall reaction when you add them together equals the overall reaction. And B, the rate law for the slow step in the mechanism does match the rate law that you find experimentally. Any questions on that? So this type of mechanism problem is a common one. Again, you sort of have to use the other steps to find the intermediate, substitute in, do a little bit of math, and that way you could again compare sort of apples to apples in this particular case. Any questions on that side? All the K's really cancel because ultimately, again, although in this particular case, there is a K here, right, as well. If I can get the K to right. All these K's, this K, this K, this K, even though they have like a little different subscript or something like that, they technically are all rate constants for this particular reaction. And if you remember earlier on in this chapter, the one thing that is a constant value for a reaction at a specific temperature is the value of K. So although we don't know what it is, all three of those numbers technically should be the same number. And that's why that when we get two of them like this, they technically should cancel out. And it really just leaves you with the overall rate constant for the reaction. Other questions on that? Okay. So let's just finish up talking about one more type of mechanism problem. I know we're at the end here, but a little crash there kind of put us just a second behind. So might as well just finish it up here. When we look at another type of mechanism problem like this, which I can't even see on my screen because I don't see it, but let me write what it is maybe. We have step one, which is a plus b to the 2 goes ab plus b, and this is slow. And number 2 is a plus b goes to ab, and this is fast. So what we want to do is determine the overall reaction. We want to determine the rate determining step. And we also want to identify all the intermediates in this following sort of mechanism. So we'll start with the first one, which should be easy. Again, we're just going to add these together. In this particular case, it looks like B will cancel. And that looks like it. So that will give us 2A plus B to the 2 goes to 2AB as our overall reaction. That also means that the only thing we canceled out was B, and that would mean that B is our intermediate. And as we talked about, since it's labeled slow and fast, that means that our slow step is our rate determining step. Is step number 1. And because that one is our rate determining step, we could actually use the rate law for step number 1. And that should be, if this is a good mechanism, which we're assuming that it is in this type of problem, that the rate law for the reaction should be the same one that you would have for that step, which would be the rate is equal to K times A times B to the 2. And we do see that is the stuff in the overall reaction, so that's all good. And here, again, would be what we would determine should be the rate law for this particular mechanism. Any questions on that there? So in the previous one here, in the previous one here, the rate determining step is step number 2, and it is because it is a slow step. But just to remind you that step number 2 actually did match the rate law to the one found experimentally. So it is the rate determining step, and it is a good mechanism. Again, it didn't initially match because we were comparing something that had an intermediate in it, like this guy. But once we were able to get rid of that intermediate and substitute in something else that's in the overall reaction, we were able to really see that it did actually match, and it was actually, again, the rate determining step because it is a slow step. So pretty much if it's labeled slow, you pretty much don't have to think about it. It's going to be the rate determining step no matter what. The second thing that you have to think about in that sense is, does the rate law really match or not match to determine if it's a good or bad mechanism? Let me just take a look at some of the other questions. The rate law does need to match the overall reaction in the sense that it does usually need to contain things that are found only in the overall reaction, I guess, if that makes sense, to maybe answer that question. you do use the coefficients as the exponents when writing rate laws for elementary steps only in a mechanism problem. Again, you do not use the coefficients like we did in problems like we did before we got to mechanisms. But when you're dealing with mechanisms, and more specifically, when you're dealing with elementary steps, you can and should use the exponents, the coefficients as the exponents. But you should not use those coefficients as the exponents anywhere else. It is, just think about it this way, it's only specific for when you're dealing with mechanisms. You should use those coefficients as the exponents. Just like we did before, like if you have a table given to you and it's not a mechanism problem, you should not use the coefficients. I think I got pretty much everybody's question, I think. Okay. Any other questions on mechanisms here? So as you can see here, there's a few different types of mechanism problems. One like this one here that we're looking at right now, again, more of a math sort of approach. And the goal is to try to figure out, is it a good or plausible mechanism or a bad mechanism? One like the other two where, you know, you're just trying to figure out what the rate law would be if they tell you, you know, this is the slow step, then it should have the same rate law as the slow step. And like the very first one that we did, which was over here, where they really don't tell you the slow or fast step, but by figuring out the rate laws for each of the steps, you could find one that matches and you'll be able to determine which one was the rate determining step. So that's sort of three different versions of mechanism problems that you can usually come across. Any questions on that there? Okay, so I think we will stop here today. We're pretty much, to be honest with you, pretty much done with this chapter and the class almost. We're going to talk just a minute or two probably on Monday in terms of catalysts, just to really officially finish out the class. But pretty much we're done with it. So congratulations on the material. But we'll officially finish this chapter on Monday. Give us something else to talk about, I suppose, on Monday. And then we'll officially be done. Reminder that I think coming up next week is a busy week. We got an exam on Tuesday. We got final exam on Thursday. We get official summer vacation on Friday, right? So that's good. So we got a lot going on. So make sure you stick up with or stay up with everything that's happening. What was I going to say here? The plan probably for next week, since we really don't have too much official lecturing to do, if you think it would be beneficial, maybe we'll just do some reviewing. Maybe I'll just kind of start from the beginning and roll through and, you know, kind of cover some of the main points, highlights of, you know, the different sort of topics and stuff that we covered throughout the semester. So that's probably what's going to be on tap, I think, in terms of lecturing part. And maybe we'll have a day if you have questions or something like that, you know, you could ask them and stuff. All right, any questions on any of that stuff? We do still have one more lab to go, which is today's, the final lab, 26 maybe? I feel like 26 in my head for some reason. So it is a kinetics experiment. So we'll do the same thing like normal. We'll talk a little bit about it at the beginning, and then we'll watch the video. You'll do the calculations. You'll have a weekend and all that good stuff. Yeah. So obviously we went way long here today. So why don't we start about 3:15, yeah? And then we'll take a little break and start at 3:15. Yeah. All right, I'll see everybody in just a second. And just to answer your question really quickly, just, you know, it's going to cover probably the main topics and stuff that we talked about. So, you know, old exams would be good. Going over examples we did in class, when you think back on topics, what things were kind of important topics, you know, those are probably a good way to study for it. All right, I'll see everybody in a bit.